So going ahead in the schedule, now we have two exciting case studies which talk about how standards, how you can do research work with combined with standards. They take the so one of them is about Wi-Fi and other about from sensors perspective. So the first speaker is Dr. Sundaram Vanka from IIT Hyderabad. I'll just briefly introduce Dr. Sundar. So Dr. Sundaram Vanka is an associate professor at IIT Hyderabad. Before joining IIT Hyderabad, he was with Broadcom, which is a main manufacturer of Wi-Fi chips. Prior to that, he has done his PhD from University of Notre Dame, similar at the same time when I was also a student there. He obtained his BTech and MTech degrees from EE department at IIT Madras. So I would like to welcome Dr. Sundaram Vanka to give his talk. Professor, Dr. Sundar, you have about 18 minutes for the talk and about 2 minutes for the questions.
Sure. First of all, thank you very much, Professor Ganti, for the kind introduction. Let me share my screen just to make sure that maybe everyone can see it. Can everyone see my screen?
Yes. Yes.
Okay. Thank you. So, yeah. Okay. So, yeah. Good morning, everyone. As Professor Ganti mentioned, I'll take up a case study of Wi-Fi standards in this talk. And what I want to convey in this talk is an idea that we can look at this 802.11 as essentially a building set, right? I mean, like a children's building set, right? Where different types of technologies and different types of ideas are developed, and they're adapted in different ways and forms in different standards that form part of this family, and they can be used for very diverse applications. So that's one of the key takeaways from this talk, if you will, right? So as we all know, I don't need to tell this audience that it can be harder to just pull out the wires. So the talk consists of three parts really. First, I want to kind of take the audience through the IEEE standards process very briefly. The reason is it gives a good context to how what are the research entry points that people can expect in this process. So this kind of stands in slight contrast to the ITU 3GPP-led model that we've seen earlier. And I will do a case study where some two key technologies were kind of taken from a more research stage to a standards phase. And then I'll talk briefly about some open problems in Wi-Fi and how it's evolving into the future. Okay. So the moment anyone talks about IEEE 802.11, I just want to break it down. So IEEE, as we all know, is the Standards Association, is an SDO. It has a SA, which creates standards for different types of industries. So we are all in this audience familiar with networking standards, but there are also floating point standards. There are also the serial bus interface standards, and there are many other standards which fall under the IEEE umbrella. And for the sake of this talk, we're interested in IEEE 802 family of standards. And there is something called the IEEE LAN-MAN Standards Committee, which is essentially abbreviated as LMSC. And it has several working groups, and each of them has a different focus area, right? So we would have heard of Ethernet, that is 802.3, and you have 802.15, 16, and 11. So 802.11 is what is wireless LAN, which will be the focus of this talk, and it's also called Wi-Fi. And the 802.11 working group, in turn, creates several study groups and task groups, which create what are called amendments to the 802.11 standard. And these amendments are not necessarily in succession, because it's not that one amendment supersedes another amendment. So these are more, you can think of them as variants created out of a common tool set. Okay, we'll come to that in a minute, right? So the approval, the way the standard is developed is as follows. The IEEE 802.11 working group has a broad representation from various stakeholders. It can be, in a lot of cases, it can be companies, it can be academia, it can be research labs, it can be government organizations. And they may have an idea or a technology that they want to essentially create a standard out of. It can be, for example, let's say if you go back 20 years, let's say you were Bell Labs and you wanted to standardize MIMO, right? So they go through what is called a project approval process. What this means is the working group creates a study group of interested parties. It can be companies, like I said, academia, government labs, and so on. They study the feasibility of a technology and chart out in broad contours what they want to achieve as part of the standard. And it goes all the way to the IEEE Standards Board, which gets approval. So it is called a project authorization request, and it's put up and it's approved. Once it's approved, the working group creates what is called a task group. And that's when you try to develop a draft standard. And this is done in a very collaborative manner. There are, just like many other standards, there are successive plenary meetings and discussions among different stakeholders. And the idea is all recommendations need to be incorporated. So there is a voting procedure. And the key idea here is consensus. So there is a 75% bar. So if participants in a given, for a given poll, there is more than 75% acceptance, that's when a certain spec or a certain requirement becomes part of the draft. And after a lot of iterations, the entire draft is created. The task group takes the responsibility of creating a draft, and it's put to vote. And once it's approved by vote, again 75%, it goes to what is called a sponsor ballot, which is run by the LMSC. And once it's approved by the sponsor ballot, and it's more or less an administrative process where it goes through the final approval, and the standard stays active for 10 years. And after which it may be either replaced or it may be modified, in which case it becomes a new project and the whole chain repeats itself, right? So that's how you end up getting this alphabet soup standards where everyone has an idea and they come up with some new way of doing things. So it started all the way with 822.11b that you see on the extreme left, maybe 20 odd years ago. And it continues to this day. And you can see various families of standards. So the ones which are shown in yellow are all networking standards. So these are all essentially LAN cable replacement, right? So they started out with 11B, they went with OFDM, then they brought in MIMO, then they brought in wider channels. And you can see the latest one, which is 11AX, which is high density networks, right? And it is now going to morph into Wi-Fi 7, right? And you can, at the same time, while these are being developed, there are other standards. Like, for example, there was one standard for vehicular communication. There was another standard for white spaces. There was another standard for IoT devices. All of these were created at about the same time as these other standards. And you will see later that there's a lot of borrowing between each of these standards. So, and now there's a new applications of wireless, which which are not really the comms application, which is more to now, which is people are talking about ranging. People are talking about sensing the environment and so on. We'll come to that also later in the talk. So that's the gist of where things are going. And this kind of reinforces the idea that I want to bring out, that this IEEE 822.11 is essentially an ever-evolving tool set, right? You can create different types of buildings, you can create different types of blocks. So you can try to create new techniques which kind of create another new type of standard, right? So that's the core idea that is good to bring in. So if you go look at 822.11ax, the Wi-Fi spec, right? If you look at the component parts, you will see that they were derived from various other standards. Some of them are not related to real networking in that sense, right? So for example, the target wake time feature was brought in as a pure power save feature, and it was brought in a big way in 11ax, and it was made into a core feature which saves power, right? And there's a lot of other new features which are brought in specifically for 11ax, such as spatial reuse, traffic aggregation, and so on. And there were a lot of older features which were enhanced, like, for example, MIMO or MU-MIMO and so on, right? So that's how you end up building the entire standard using several tried and tested technologies which have been deployed at scale, right? So this gives us a right segue into jumping into the Wi-Fi 6 development, which, like I said, if you just go through the original flow that we just discussed, there was a study group which was called the High Efficiency Wireless LAN Study Group. It was formed way back in May 2013, and it was approved by May 2014. And a lot of research activity focused on actually figuring out what should be the contours of the standard. And that is where a lot of academia, industry, and research labs were involved. And once that got approved, you actually have a kickoff where there are regular meetings, just like we saw with Professor Karandika's presentation. There's a lot of ITU meetings, right? Similarly, you will have IEEE meetings where a lot of new proposals are discussed and a lot of new IP actually is generated that way, right? We'll come to that in the later part of the talk. So then it was put to ballot. In fact, it failed the first ballot. Several iterations later, it passed. And eventually, you will see that by May 2021, it was published. But if you see way before that, sometime in Q3 of 2016, the first chipsets were actually produced, because many companies felt that it was close enough to the final product that they were comfortable putting money and making silicon. Okay, so you can see that the standards timeline is not as fast as the product timeline, but the due process is followed for every standard. So why did this due process take that long, right? The reason why it took that long is essentially because they were trying to have an evolutionary leap in Wi-Fi. So the Wi-Fi originally started out as a very simple, low density, sporadic kind of traffic network. So they tried to use it for essentially browsing, right? So if you looked at maybe 20 years ago, you would find someone like Amitabh Bachchan using it, right, for his own fancy thing, right? But as it evolved, as smartphones came up, people started using Wi-Fi in a much more wide sense, and you started needing more bandwidth. And with the evolution of Wi-Fi into more ubiquitous usage, you will need a lot more care in designing protocols that have low interference and low overhead. And these are the two main topics that were sort of have a very big overlap, in fact, with a lot of ad hoc network kind of literature. So that kind of informed a lot of initial work that went into dense network deployments. So in fact, a lot of empirical studies were also done. And this one, for example, I'm showing here is done by Aruba Networks. So what they did was they took a simple access point and they connected many clients. As they kept increasing the number of clients, and they asked each client to do a TCP upload. They found that if you look at the sum throughput, if each client is transmitting in turn, you would see that the sum throughput should be approximately the same, because everyone is transmitting the same thing, right? But what happens after a while is some clients do not get to transmit, and in fact some clients drop their transmission rate or even the packet size. So this leads to a series of events which leads to a very rapid roll off in the throughput that you see, the sum throughput that you see to an AP. And this therefore shows that you cannot have the CSMA type protocol, which Wi-Fi does, to really have a massive uplink, right? So a solution to that was essentially to look at the collision problem, where two clients or stations, as they're called in IEEE, try to talk to the same access point, and they end up colliding. So the reason why it was developed was it is highly simple, but then the flip side is it is highly ineffective. So the option that the standards body took is they moved all that access to the access point and essentially made it more like an LTE like a system, right? You try to have one AP that does that tries to coordinate channel access throughout its own network. And that obviously improves overhead and also makes sure that these collisions are reduced, right? So another important consideration that very rarely shows up in a lot of literature outside Wi-Fi is the fact that normal networks, if you go and look at residential deployments of wireless networks, most networks have very uneven frequencies. So it's not that my neighbor has the same bandwidth as I do, and it's quite possible that our channel, my channel, and my neighbor's channel overlap. So this is what is called the overlapping BSS problem, which is a very well understood problem in Wi-Fi, in the sense that it has been there ever since they started increasing the bandwidth. The problem with that is, although Wi-Fi really operates on free spectrum, it can get really congested. In fact, a lot of the spectrum in the 5 gigahertz unlicensed band is forbidden to use unless there are some very sophisticated radio detection algorithms that are running on the chip, which most vendors do not do. So as a result, you will have situations where, if you look at this example, there's a network that really needs the 80 megahertz bandwidth, and it has 5 client devices, and there are these smaller networks that use smaller bandwidth. And what the end result is, all these networks happen to overlap in frequency. Remember, this is unplanned deployments, which is usually the case in many cases. And as a result, what happens is these networks essentially end up hogging the whole of the channel. And if you look at the time versus frequency, the frequencies available to the yellow network are only in this shaded region. And what this means is regions which are like this can't be used because there are parts of the channel that are already being used. So it's all or nothing kind of usage, which means that it is going to be inefficient. So one of the key contributions of some of this work is to try to increase the usage of spectrum, and in a more opportunistic and in a more flexible way. Okay, and that kind of led us to develop more algorithms which went into Wi-Fi 7. I'll come to that in a few minutes, right? So the idea is you reclaim more and more spectrum by allowing APs or in general client devices to access spectrum provided they lower their power. Okay, and they are able to stitch together non-contiguous subchannels. And the key challenge here is how do you do it in a very decentralized manner? And there are obvious benefits to that, but of course there are obviously some pitfalls because of the decentralized way in which we do it. So that kind of sets the stage to what can be done beyond Wi-Fi 6, right? So if we see today, a lot of Wi-Fi 6 use cases are connected with very large deployments. So if you look at a large office or a large stadium or a large railway station, you will see a lot of Wi-Fi deployments, and that is the use case that Wi-Fi 6 was meant to solve, right? Now, if you move forward, let's say by 4 years or 5 years, one of the key challenges that Wi-Fi will see is the fact that people really want higher throughput, but possibly at lower latency, or even maybe not, if not lower latency, they want greater reliability. So think of a video, right? You want to make sure that you don't have too much latency when it comes to an AR/VR kind of a scenario, right? Or if you want to have IoT, you may not care too much about throughput, but you may really care about latency, right? So this kind of ties into this URLLC theme that you see in 5G, or MMTC, right? Theme that you see, and there's a Wi-Fi's own take on it and how they want to address it. So they try to have several techniques to do, and I'll discuss a few of them here, right? First technique that people try to do is a more advanced way of trying to use non-contiguous frequency allocations, both in the uplink and downlink, and also in the peer-to-peer scenario. So the idea is you sense the medium and you kind of learn what parts of the channel are busy and what parts of the channel are free, and try to use non-contiguous chunks of spectrum. This can happen both for the access point as well as the client devices, right? So that increases efficiency, right, in a way. And added to that, you can think of this non-contiguous usage, and you can take it up to the next level. You can imagine that instead of trying to have one band and one channel, you can imagine that each band can be thought of as a queue, and you can essentially merge, traffic. You can take traffic from a queue, and you can use some kind of a statistical multiplexing approach to try to get the best out of two possible links. The idea is both the queues kind of merge at the top of the MAC, right? So that's called multi-link, and that's another thing that is being really explored. Another slightly more complex scheme is what they call multi-AP coordination, where different access points talk together and they try to serve a given area. It is more something like coordinated multi-point or network MIMO, right? But with spin that these access points have a limited coordination overhead, right? And you don't have a wired backhaul, for example. That could be one of the requirements, right? So you can have something like multi-AP coordination. So the one I showed here is essentially, something like network MIMO. This is essentially, coordinated nulling, right? Or coordinated beamforming, whichever way you want to call it. But beyond that, the open problem is it's not even clear what are the best ways to actually scale this, and what is the best way to achieve these so-called low latency targets, or so-called, high reliability targets that Wi-Fi 7 has set for itself. So that's kind of an open question, because all these things get together are, they can form a very complex interaction, right? And beyond Wi-Fi networking, there is also this idea of sensing. So one of the key paradigm shifts that happened recently is this idea that you don't want to use a wireless network to only send information, but you also want to detect something about the environment. And that is called Wi-Fi sensing, right? So the idea is, traditionally, when you take any wireless connection, you are going to have transmitter and receiver. The idea is to use changes to this channel state information to figure out if there is a change to the environment. So that can be used, obviously, for surveillance right away. And you can see that it has applications in various scenarios. For example, it can be used for safety monitoring, smart buildings, or even gesture control. So with that, I think I hope I gave you a flavor of some of the work that goes on in Wi-Fi. Thank you very much.
Thank you, Dr. Sundar. It's very nice to hear about the standardization activities in Wi-Fi and how we can contribute to the standardization activities. I think there will be a lot of questions. I mean, what I request is that people type in their questions, and Dr. Sundar can answer these questions on the chat.